Hey guys, in this particular video, I'm going to define work, and I'm going to bring you through an example problem so you understand just how to apply the work formula. So what is work? Work is the amount of energy being put into an object via a force to make the object move a distance in the direction of the force. And this can be mathematically represented too. The energy I'm talking about is just this. W is the energy, also denoted as work, is equal to the integral from state 1 to state 2, and I'm going to tell you exactly what that means in a second, of your force vector dot product with your differential displacement vector dr. And I'm going to walk you through exactly what these mean, and I think the best way to do that is probably through an example. But for now, a force vector can only be in 3 dimensions because we live in a 3-dimensional universe. So it's going to have the components of fx in the x direction, fy in the y direction, and fz in the z direction. So basically, if you've got a force vector pointing in some direction, you can always reconstruct it in these 3 dimensions, and as such, you can rewrite your force vector like that. Not only that, but your differential displacement vector, dr, is defined to be equal to this. It's dx in the x direction, dy in the y direction, and dz in the z direction. So basically, it's just a small bit of movement in all 3 dimensions. It's just a really small differential vector right there. So let's go through an example problem so you guys can really understand how to apply this formula. Well, I think the most simple example we can use is probably a block being slid across a surface. So let's say we've got this block lying on the ground right here. The ground doesn't have to be frictionless in this example, and I'll tell you why in a second. And let's say we're applying a force, an external force, on this block by, say, pulling it at an angle theta above the horizontal. And I'll define the horizontal as being this right here, our x-axis just here. And so this is your angle theta, and this is your force vector right here, and I'll just call your force vector, I'll say it's got a magnitude of 10 newtons. So your force vector is 10 newtons in this direction at an angle theta above the horizontal. And also say, as a result of you pulling this object, the block has moved, let's say, a distance 2 meters. So in other words, the block was initially here, you apply the 10 newtons force, and while you're applying this constant force at an angle theta above the horizontal, the block has moved 2 meters. So this makes this your displacement vector. This is your displacement vector, r. And this is your force vector, F. Alright, and before I get started, I just really want to mention that there are other forces acting on this object. I mean, there must be, right? I mean, you're going to have a force due to gravity down here, and you're going to have a normal force up here, and perhaps if the floor has got friction on it, you're going to have a friction force opposing motion like this. But for now, and even if we do consider these forces that are acting on this object, let's say we're only interested in the force applied, in the work being done by our force, our 10 Newton force. So in other words, we're only interested in the work being done by the 10 Newton force. So even though there are other forces acting, we just don't mind. We're just calculating the work done to this force alone. Alright, let's get started. Well, for starters, we need to reconstruct our force into our x, y, and z components. To do that, we need to have a better understanding of what theta is. Let's say theta is, I don't know, let's call it 60 degrees. 60 degrees. Right, so let's reconstruct F in x, y, and z. Well, to do that, let's just draw a triangle and do basic trigonometry. So we know this is our force, this is our horizontal component of our force, and this is our vertical component of our force. So the magnitude of our force is 10 newtons, and it's at 60 degrees from the horizontal, implying that the magnitude of our x component of our force is just going to be 10 cosine 60. And using trigonometry, we can also determine that the magnitude of the y component of our force is 10 sine 60. Notice I say magnitude. because I haven't multiplied this by the I, j, or k unit vectors. This is just a number. It's a scalar, right? But if I did want to consider direction, I would multiply it by the I unit vector or the j unit vector. Alright, so as such, we can say that your force vector, I'll just write it down here, your force vector here is going to be equal to, well, it's going to be 10 cosine theta, or cosine 60 in this case, cosine 60 I, that's your I unit vector, so showing that it's in the direction of the positive x-axis, plus 10 sine 60 times j, and that's showing that you that it's in the positive y direction. All right, and I should also mention, because this is a three-dimensional universe, we've also got plus 0k. And the reason why there's a coefficient of 0 there is because this force has no component in the z direction at all. Remember, the z component is acting out of the page and into the page. To make this more clear, I'll even draw a set of axes on, which is probably something I should have drawn earlier. But here's our axis. Let's choose our axis such that it's going straight through the center of mass, just for simplicity's sake. So our axis is here. This is y, and this is x, and z is going out of the page, which implies that this is your j unit vector of magnitude 1, and this is your I unit vector of magnitude 1. But anyway, I don't want to get caught too much up about definitions of unit vectors and whatnot in this video. Let's try and burn through this particular type of formula. Alright, so let's sub it in. The work done by our force we're applying on the block is going to be equal to the integral of state 1 to state 2 of our force vector, which we know can be redescribed as 10 cosine 60. Should probably simplify the cosine 60 soon. And then 10 sine 60 in the j direction, and 0 in the z direction, as we previously discussed, multiplied by your differential displacement vector, dr, which I previously wrote down was just dx, dy, dz. Alright, we're getting there. Let's try and figure out what this goes to. Alright, well, we know by the definition of the dot product that if we've got two vectors being dotted with each other, you multiply the top two scalars and then add them to the multiplication of the next two scalars, and so on. So maybe that'll be a little bit more clear when I just write it out. That'll be equal to the integral of 10 cos 60 dx plus 10 sine, let me fix that up, 10 sine 60 dy plus 0 times dz. Alright, and this is still from state 1 to state 2. Alright, well, we know that the integral is distributive if we've got a plus and minus sign in between them. So what we can do is we can split this up, right? We can split these terms right here. So this is the integral, and this is an integral right here, but because this is 0, I'll just get rid of it. Don't worry about that for now. And as a result, what I mean by state 1 to state 2 are our limits of our displacement. So this will be from, because it's dx right here, this will be from x1, our starting position in our x coordinate system, to our final position in our x coordinate system, which I'll call x2. Likewise, because this is dy written out here, this will be from y1, our starting y position, to our final y position, which I'll call y2. Alright, let's see if we can simplify this a little bit more. This becomes simple algebra, with the assumption that, well, actually, because we know our force is constant at 10 newtons, and this is entirely a constant, we can just actually bring that outside the integral sign. So this becomes a really easy integral to evaluate. This becomes 10 cosine 60, should really evaluate that cosine 60 soon, times by x2 minus x1, plus 10 sine 60 times by y2 minus y1. And you know what, I will actually write the plus 0 dz here, so you know I'm not fudging anything. This will be the integral from z1 to z2 of 0 dz. And we all know that's just a constant when you integrate 0, so that's just going to be plus some constant with limits from z2 to z1, z2 to z1, sorry, z1 to z2. And of course, if you evaluate this, that'll just become 0, because a constant minus a constant is, that same constant is still 0, so it'll become 0. So that's a proof right there. Alright, so now that we've got this a little bit more simplified, let's see if we can finally solve the question. And to do this, we need to figure out what x2 is, x1 is, and y2 and y1. And to do that, let's look back up at our problem. Alright, because I chose our axis to be right here, right there, we can see that our x1 value is our initial starting position in x. x1 is going to be 0, and y1 is going to be 0. Actually, purely out of definition, because I chose my axis to be there such that x1 and y1 were 0. But look at x2 and y2. It's moved 2 meters to the right. Consequently, x2 will just be positive 2. Right? And sign does matter in this. It's moved to the right in the positive x direction. And y2, let's see what's y2. It hasn't moved horizontally at all. There's been no change in vertical displacement. Consequently, y2 is going to be 0. Alright, well, keeping this in mind, let's see if we can evaluate what we had below. Well, this will evaluate down to 20 cosine 60. Still haven't evaluated that cosine yet. 20 cosine 60 plus 10 sine 60 times 0 minus 0, which is just 0. Right? So in other words, y2 minus y1 is just 0 minus 0, so that's going to be 0. x2 minus x1 is 2 minus 0, so that's just going to be 2. So you can see how I got this value right here. That is that right there. And that is that 0 right there. Alright. And for the sake of completeness, I'll also put the 0 for the z component too. Alright, well, let's see if we can evaluate this a little bit further. This becomes simple trigonometry. And let me just remind myself on trigonometry. So let's see, this is 60, so that'll be root 3, that'll be 2, that'll be 1, so that means cosine 60 will be a half. Alright, so that's just, so what's that? That's 20 times by a half. So we're going to have 10 Newton meters, because our work is in form of Newton meters. And if you don't believe me, we can just look up back to our definition. F is in newtons. dr, because the displacement is in meters, and even if you integrate it, it's still going to be Newton meters. So consequently, our work is in terms of Newton meters, or by definition, 10 joules, right? Where 1 joule is just 1 Newton meters, in 1 Newton meter, which is also a unit of energy. Alright guys, I hope that example made a little bit of sense. In the next video, I'm gonna tell you how to work out work using just the knowledge of a change of speed.